In this part of the lecture, we will look at how we can extract data for a process from a process flow sheet. Data extraction involves the collection of data for process and utility systems, and to apply pinch analysis, we need information about the streams in the process that require heating and cooling, and also about the available utilities. So when you are designing a chemical plant, you have the data for your plant calculations, or you have the data from data acquisition system or your simulation model for the whole plant, and you have huge number of streams and a large amount of data. So it is important to understand how actually we can extract data that is relevant for the process in terms of the pinch analysis. So when you performed a design intensive week, you simulated your data, and most of that data for the hot stream and cold stream of your process and the conditions were given to you, and your main goal was to develop, for example, a hand network to minimize the energy consumption or to maximize the energy recovery. But now you are the design engineer, and it means that you have the power to change those values of temperatures or conditions, and you can also change your process. Okay, so you can decide if you want to use a particular heat exchanger or not. Okay, and once you make those changes, then you again build your composite curves, and you from those composite curves you define your energy duties or energy targets, and then you can compare between different designs, that which design is the best in terms of the minimum energy target or the area target. So as I said that for a process, now we need to identify what are the hot streams and what are the cold streams and what are the relevant temperatures that we need to extract from this process. Okay, so we start from an existing process, and then we extract data, and then we perform heat integration analysis, and then we can compare the heat integration between different designs, and based on that we develop a new process flow sheet. Now the data for each process stream consists of the mass flow rate of the cold and hot stream, their specific heat or their heat duty, and then the target supply and the target temperature of hot stream, and the supply and the target temperature of the cold stream. And if you have vaporization, then we need the latent heat or heat of vaporization for the phase change in terms of the data for the process stream. Now there are some guidelines based on which the data should be extracted. So in the next few slides we will go through those guidelines. So the first guideline is that process streams that experience heating or cooling should be extracted. It means that we need to know what are their supply temperatures, target temperatures, and heat capacities of all the process streams. But we do not extract utility streams. And utility streams are like, for example, steam, cooling water, refrigerant. And the reason we do not extract utility streams is because that the quantity of utility stream is normally that we calculate or we find out by designing the heat exchanger network. Okay, so we don't need to extract them in advance. We find that duty at the end of the design of our heat exchanger network. So for example, here we have cooling water as cold utility, and here we have MP steam as hot utility. So we don't need to extract them for pinch analysis, because these are external utilities, and the value of these utility streams are dependent on our heat exchanger network design. But there is an exception. So if a utility, for example, here we have LP steam that is used in the process directly to enhance the efficiency of the reaction or efficiency of this process. So for example, here steam is used in the shift reactor to again to enhance the efficiency of the reaction. So we can extract it, because this stream is not a utility stream anymore. It is now part of the process, and we treat this steam as our process steam, and then we need to extract it. So to summarize, we need to extract all the process hot streams and cold streams. We do not need to extract the data for utility streams unless that utility is directly involved in the process, and then we treat that utility as a process stream, and then we extract the data for it. Now, the second rule is that one should identify hard and soft constraints on temperature, pressure, and enthalpy levels. So, for example, a hard constraint would be the inlet temperature of a reactor that cannot be changed in any way, because if you change the reactor temperature, you are going to change its reaction conversion, the yield, and as such, you are going to change the whole process in terms of separation and the recovery of the product as well. While on the other hand, a soft constraint would be the discharge temperature of a storage tank, or the product temperature that you want to store at. So these are very much flexible, and we can change them to improve our system. So here we have an example where we have a stream is going from a temperature of 500 degrees centigrade to a final temperature of 100 degrees centigrade, and we have a couple of exchangers, three exchangers, and then we have one cyclone here. So when we are extracting the data for this process, we don't really need to fix these intermediate temperatures of these exchangers and around the cyclone, because these are considered as soft constraints, because we are mainly interested in this stream going from 500 to 100 degrees centigrade, and then we want to recover the intermediate heat between these two extreme temperatures. Okay, and also we don't really need to fix the number of exchanges in this stream, because that depend on your Henn network. So once you have the maximum energy recovery, the Henn network will dictate what are the intermediate temperatures or the temperatures around these exchanges. Okay, so we extract this stream, this whole stream with different temperatures as one stream going from 500 degrees centigrade to 100 degrees centigrade. So the next rule is about stream mixing, which suggests that if you have two streams at different temperatures, we should not mix them. Okay, so here, for example, if you have this system where you have one stream going from 25 degrees centigrade and is being mixed in a stream that is coming at 200 degrees centigrade with a target temperature of 140 degrees centigrade, we should not actually mix these streams, and we should not extract the data as three different streams. We should treat them as two different streams going from 200 degrees centigrade to 140 degrees centigrade, and then the other stream should go from 25 degrees centigrade to a target of 140 degrees centigrade, and then we can recover the maximum heat from a hot stream to a cold stream. Another issue of mixing streams is that you might end up in a situation where you have actually heat transfer across pinch. And if you remember from process integration, if you have heat transfer across pinch, you end up increasing your hot and cold utility. So that is not, again, a good situation for our process in terms of energy recovery. And another part of this heuristic or this rule is that if you have to mix two streams for whatever reason, then first you should bring those streams at the same temperature and then mix them. So for example, here you have two streams at two different temperatures. So first you bring them to same temperature and then you mix them. Okay, so although this is seems like mixing, but actually because they are at same temperature, so although the stream is mixing, but the actual heat transfer at this point is zero because they are at the same temperature. So again, the idea is that you extract or recover all the possible heat from hot and cold streams, and then you can mix them at isothermal conditions so that there is no heat transfer between the different streams. So here is a self piece for you for extracting the data for a mixing system for this given system here. So try to think that how you would extract data for your pinch analysis, and we will discuss the solution in synchronous session. So the next rule is about effective temperatures. So some temperatures in your process you might not want to change because those are the hard constraints. As I explained you in the case of a reactor, that we don't want to change the inlet condition of a reactor because it is a hard constraint or effective temperature in terms of the best conversion or the best yield. So we don't want to extract that kind of data. And similarly, here we have an example of a distillation column, and this distillation column is operating at 140 degrees centigrade, for example, inlet feed. And we might not want to change it because this temperature might be based on the optimization of this distillation column through the design. Okay, so in this case, we just want to keep this temperature fixed, and as such we will not extract it for our heat recovery or pinch analysis. The next rule is that we do not extract stream data where there is a negligible contribution in terms of the heat duties. So for example, the stream here is going from 90 degrees centigrade to 80 degrees centigrade, and the heat duty of this exchanger is 0.05 megawatt. So even if we extract this data, it is not going to make any significant contribution to the heat recovery of the system. And another reason that we do not extract streams with negligible heat duties because you are designing a whole chemical engineering plant and you are going to have hundreds of streams. So if you extract data for all these small duty heat exchangers, you are going to have a lot of additional data to process, and that is going to take a lot of engineering time. Okay, so you want to make your life easy at end of the day, and then you can neglect these small duty heat exchangers in the initial analysis, and then later at the later stages of your design you can decide if you want to extract them or not. So the next rule is that we do not extract data for enforced matches, and enforced matches are mostly you can see them in retrofit designs. Okay, so for example, this is an existing system here, and you can already see that the heating of this stream that is going from 40 to 150 degrees centigrade is actually the heat is provided by the cooling of this stream here, the product stream that is going from 180 to 80 degrees centigrade. Okay, so there is already a match here. It means that this system is already in sync, so we don't need to extract this data for pinch analysis or for heat recovery. So the last rule is that how we can approximate a stream with non-linear CP. So for example, we know that CP is a function of temperature, as you can see in this equation, and if you have a large range of temperature like that is the case in our processes, so we might have a situation where the stream has a non-linear CP, and that non-linear CP can be represented on this temperature enthalpy diagram here that is shown with this red line, and we can approximate this non-linear behavior or non-linear CP with these constant CP lines as by these straight lines here. Okay. Now, if you focus on this circle area here, you can see that if you have a hot stream here, that is the red, and let's say green is your cold stream, so the actual hot stream can very well exchange heat with this cold stream here, while the approximated stream cannot, because the approximated stream is already below the green cold stream. So it means that this is a false low temperature, and obviously we are going to lose a lot of heat recovery opportunities here, and also it is going to create error in our HAN analysis in terms of energy recovery. So this rule guides us that how we can approximate the stream of a non-linear CP. So the rule is that if you have a cold stream, you approximate it with a linear stream where the cold stream is actually colder than the linear approximation. So as you can see here, so your actual cold stream is colder than the linear approximation. So that is for the cold stream. And for the case of hot stream, the rule is that we linearize our CP in a way where the actual hot stream is hotter than the approximated hot stream. And also we try to approximate it as close as possible, like as you can see here, not what we have in the previous slide. So let's have a look at this worked example and try to use the guidelines that we just learned and see that how we can extract the data for this given process here. Okay, so we need to extract data in terms of the supply temperature, the target temperature, the heat load, or the heat capacity flow rate. Okay, so we can extract one of these two, and we are also given some additional data in terms of the enthalpy and the mass flow rate of the steam. And as we know that the condensation and vaporization are isothermal processes, but in practicality actually we assume a 0.1 degree decrease to perform calculation, because if we assume isothermal conditions, we will not be able to do calculations because the simulation software will not be able to use a delta T equal to 0 for calculation. So let's have a look at how we can extract the data for this process. So we can make use of the guidelines for data extraction. And this is an overview of the guidelines we just discussed. So the first guideline is that we have to extract the data for process stream and non-utility streams. And here steam is actually a non-utility stream because it is being used to enhance the shift reaction. Okay, so we can extract the data. So we know from the question that its supply temperature is 150. We also know its mass flow rate and its heat of vaporization, so we can calculate the heat duty of this steam would be 10 times the heat of vaporization, so that is this much kilowatt, and then you can convert this kilowatt into megawatt, so that would be 21.13 megawatt. And then from the second equation we can calculate what is the Cp. Okay, so we have the delta H. Cp is unknown, but we know the temperature difference because we are given in the question that we can take a 0.1 degree drop in the temperature for condensation and vaporization. So as such, our first stream would be a hot stream, and we have all the data that is necessary for pinch analysis. Then for the second stream, we can look around this section here, where we can use the guideline of soft temperatures. And here we can take the stream going from 500 degrees centigrade to a final target temperature of 140 degrees centigrade. We don't really need to include these intermediate heat exchangers. Okay, so we can use 500 going to 140, and to calculate the delta H in Cp, so we can do energy balance here around this exchanger, for example. So we know the heat duty of this exchanger is 20, and if you take delta H 20 equal to Cp times a delta T of 100 degrees centigrade, so you can get the Cp of 0.20. And once you know the Cp of this stream, you can actually use this temperature difference multiplied by the Cp, and that should give you the heat duty of going from 500 degrees centigrade to a final temperature of 140 degrees centigrade. Next we have the stream mixing. So here again we are not considering the mixing of these non-isothermal streams, so we are going to take them as separate. So here we are going to use a stream going from 25 degrees centigrade directly to a target temperature of 140 degrees centigrade, and that is our third stream. And we know that we can again do a Cp or heat balance around this exchanger, where we have 25 going to 80 degrees centigrade with a heat load of 1 megawatt. So if you do the Cp calculation from this, that would be 0.018, and then you can calculate the final heat duty of this stream going from 25 to 140 degrees centigrade, multiplying by this Cp. So we have the heat duty of this stream here. Then we have the next two streams related to the condenser here and the reboiler here. Okay, so for the condenser, it's going from 60 degree centigrade condensing, so there is a drop of 0.1 degree centigrade. For the case of vaporization, we have an increase of 0.1 degree centigrade. So we know both these temperatures. We know the heat duties of these exchangers already. So we just need to calculate what is the CP of these two streams. Okay. So that is all for this part. In the next part, we will talk about energy utilities and how we can do energy recovery for a total site.